All right, good afternoon, ladies and gentlemen. I'm Bill Hamblett from the Naval Institute. I'm the editor-in-chief of Proceedings Magazine. It's great to have you all here. This should be a very interesting panel discussion, Directed Energy and Hypersonics, Emerging Capabilities and Challenges. I have the pleasure of introducing the moderator of the panel this afternoon, Commander Dave Holland. He is the Anti-Submarine, Anti-Surface Warfare Tactics Instructor and Deputy Director for Surface Advanced Warfighting School at the Surface and Mine Warfighting Development Center here in San Diego. Most recently, he was the Executive Officer and Commanding Officer of the USS Chung Hoon, DDG-93, based in Pearl Harbor, and he is a graduate of the Anti-Submarine and Anti-Surface Warfare Tactics Instructor Program. So, Commander Holland, the panel is yours.
Thank you, sir. Appreciate the introduction. And how I'd like to run this, at least on the front end, is I'm going to introduce each of my colleagues on the panel. Very wide scope of potential discussion points when you talk directed energy and hypersonics. So I'm going to ask each individual, after I just briefly introduce them, namely their title, to just give kind of a background on their subject matter expertise and how they may contribute to this panel. Starting off with Mr. Dave Keel, the Division Director for Air Warfare and Weapons at the Office of Naval Research. Dave?
Hello. I got a fairly diverse portfolio that goes from aircraft to strike and air defense weapons to directed energy weapons. My primary background is directed energy by most of the people who know me, and this distinguished young man helped educate me on it. What I'd like to do today is just kind of go through some of the pros and cons real quickly of lasers, and then what the Navy wants to use them for. So let's actually start there. The Navy really wants to be able to kill cruise missiles and then future advanced threats. Cruise missiles are probably in our bailiwick with today's technology. Small UASs are a piece of cake. We can kill them really fast. Small boats and ground vehicles, generally we don't kill them. We generally give a mission kill. We either catch them on fire so the people jump out, or destroy the outboard motors on a small boat. And then there's soft infrastructure stuff that they can do. They can do all sorts of things in the hands of the special operators out there. What are the advantages? And this is the one the Navy cares about the most, is the deep magazine aspects. As long as the ship has electricity, and the laser's not damaged by the battle damage, we can shoot it. And standard missile, ESSM, RAM, all those missiles run out after a limited number of shots. And so that's why the Navy would like some additional layers for defense, air defense, and that doesn't require things coming out of VLS, the vertical launch system. So one other advantage with lasers is they have a tendency to be a scalable effect. It's pretty easy to start making a boat catch on fire, but a fairly small spot, and not try to make it grow. And that kind of disrupts their day and stuff like that. So you can turn the power up, you can turn the power down, and there's a lot of missions you can do there. Disadvantages, laser weapons, by their fundamental nature that everything comes out of a telescope called a beam expander when you're making a laser weapon, means it can only engage one target at a time. And even though we go at the speed of light, we don't go at the speed of a kinetic weapons kill. We have to dwell on the target. We have to dwell on the target depending upon the materials and all that, probably for about 5 to 10 seconds. So you can see it's fairly easy to get saturated if that's your only weapon, and that's why lasers will never replace the other weapons. The other thing is the current state of the art with laser weapons based on the best fiber laser technology, which right now is the most reliable, dependable lasers out there, is only about a 30% wall plug efficiency. So if you want a 300 kilowatt laser, you need to pump a megawatt of AC power into it, and then you need to get rid of 700 kilowatts of waste heat. That's kind of taxing, but it is very doable on today's ships. For one reason, ships float in the largest heat sink in the world. And it's just a matter of getting it out of the laser and getting it down to the ocean. And there are many ways of doing that. The other thing that we get pushback on all the time is lasers aren't all weather. I like to remind people, no weapon is all weather. Lasers are just being held to a very high standard. The final aspect of that is every laser shot I am aware of that got canceled or postponed due to weather was because the target couldn't fly or the safety people wouldn't let us go in low visibility. The world, if you look at that picture, looks very different in the visible world, what our eyes see, and what a laser sees at 1 micron. And that's just a fundamental physics issue. We can get through a fair amount of fog. Yes, we'll be degraded, but we can get through there. And that's all.
All right. Thank you, Mr. Keel. Up next, Professor Joe Blau from the Naval Postgraduate School. Sir?
Yeah, so I've been working in directed energy research for about 30 years. I think Dave was one of our first students that came through our research group. And Dave and I didn't coordinate this too well, so this covers a lot of the same points that he has on my slide here. But most of our recent work actually has been on atmospheric propagation of the laser beams. And Dave mentioned that that's an issue, that they're not all weather. And so but how bad does the weather have to be, and how much does that affect the laser performance? That's a lot of the research we've been doing recently, including underway experiments on the USS Spruance, which I know one of our panelists actually served on that ship. And on the USS Portland, we did experiments when they were testing the laser to look at the atmospheric effects on the laser beam. So Dave already covered a lot of these points as far as the pros and cons of lasers. And I just want to mention what he said about the finite dwell time. We are doing research on that also at NPS in our physics department, looking at the lethality effects and looking at the interaction of the laser beam with different types of materials and how long it takes to cause certain types of damage effects. And that's actually what my current student, Lieutenant Commander Curran, is doing his PhD dissertation on. So I'll pass it on to him.
Okay. Next, Lieutenant Commander Brian Curran, PhD candidate in physics at Naval Postgraduate School. Brian?
Yes, thank you, sir. So just to kind of give some background of where I'm coming from. So this is actually my second time at NPS. I'm actually a repeat offender, I like to tell people. But yeah, I came through about 10 years ago, got 2 master's degrees, one in applied physics. My thesis advisor, Dr. Huber, sitting there in the back from back then. So. And also I did mechanical engineering as well. But from there, I went to Port Hueneme, where I was a BMD testing officer. So basically, hand me a missile, send me out onto a ship, and we go launch a target, take it down. And from there, I worked at OPTEV-4 for 3 years, where I worked as the operational test director for directed energy. So basically, helping design the test plans, essentially, for lasers to bring out to the fleet. From there, I went to the Missile Defense Agency, did some more BMD work. And now, as Dr. Blau mentioned, I'm working laser lethality from a simulation standpoint. So the bottom line is I have background that kind of spans between BMD and lasers for the most part. But kind of a couple things that I want to point out here is, we talk about lasers as if there's some sort of isolated system. And right now, because a lot of these are not fully implemented out in the fleet, they are. But ultimately, these things will not be. What needs to happen is these things need to be integrated into the combat system. Okay, so for example, if you put them on a destroyer, you need to be able to find a way to make it work with Aegis, and that's a major consideration. They need power, they need cooling, et cetera, from the ship to be able to operate. So basically, there's a whole lot of engineering challenges that are going to be associated with putting these on a ship that are beyond just a simple science of how does a laser work. Okay. Another thing is also, lasers are fundamentally different from kinetic weapons. Kinetic weapons, if you think about it, you're going to be having a missile flying out to a target, okay, and that's basically a non-zero process in terms of time. It's a non-zero time that it takes to do that, but it's an instantaneous effect, a missile, right? Blows up, problem solved. However, a laser is the exact opposite. A laser is much more like a blowtorch at range, okay? Where basically you have to have a non-zero dwell time of that laser on the target to actually impart some sort of effect. And so, however, conversely, you have instantaneous time on top. So basically, it also requires the users to have a change in their calculus in terms of what to expect in terms of their ability to implement this and how to fold it into a layered defense within their weapon system. And so kind of one thing I do want to point out is that because these technologies, lasers and also hypersonics, are accelerating so quickly, we do need to train officers who are going to be competent, confident in their ability to implement these as they are rolled out in the future. Thank you.
Thanks. And our final panelist, Lieutenant Commander Joe Lewis, an integrated air and missile defense warfare tactics instructor, currently serving at Surface and Mine Warfighting Development Center, Fleet Training Pacific. Joe?
Good afternoon. First and foremost, I'm not a scientist. My role here is from a end user tactical perspective. Over several tours, first as the fire control officer on a ballistic missile defense ship, then as the Webson CSO on Spruance, where we installed and then deployed with the Odin laser system. My experience lends towards, and my knowledge towards, the current challenges of fighting in 2023 in the near term and the tactics associated with that.
Thanks, Joe. For the first question for the group, we think about directed energy, hypersonics, as Joe just mentioned. We talk a lot about the current conflict and being ready to fight tonight or fight now. So for the group, is this really something that near term has revolutionized the battle space, or is this near-term impact and then medium and long-term strategic initiatives, T&E, down to being able to get the right weapon fielded in a meaningful manner to trained operators? And Mr. Keel, if you could kind of take that from what's here now and then how we see that moving forward.
If Dave Keel didn't say he thought lasers were game-changing and revolutionary, I would lose my laser membership card. So take everything I say with a little bit of bias. I do believe they're game-changing, but I believe it's a whole new way of killing missiles. And that's my primary interest, being in the Navy, is killing anti-ship cruise missiles. Historically, I'm not going to say that. Every time I've been to a laser test, it's killed the target. Every time I've seen missiles leave the rail, they missed. Except for on my final ship, where 4 Rams, in a cakewalk scenario with IR augmented targets, doing a system test out, not a real operational test, did hit the target. So I have a strong belief that missiles, because of their cost, because of their limited capacity that you can carry them on ships, lasers offers an additional layer of defense, never to replace the other missiles, but an additional layer. And I believe that is revolutionary in itself. The Navy is still going very cautiously, even though we probably lead all the other services. We have 5 Odin lasers on ships today, with 3 more coming in the near term. We have 1 Helios ship, and if you go down to the Lockheed Martin booth down there, you can talk to them and they'll tell you all about it. It was an IWS N96 program. It's on the ship now. It's going to go through its C-Squat, which is its qualifications, later this summer, I believe. And it's out there. The Navy has an S&T program that is just wrapping up called the SSLTM. I was just down at the Naval Station this morning to go look at it on the pier. Sounds horrid that it was taken off, but it was an S&T system. It could not have survived another deployment, but it did go on a full 5th and 7th Fleet deployment, came back and actually operated overseas with sailors operating it. We solved numerous policy and T&E issues with that evolution. And then we also have our Hellcat program going on right now, which is to get to the next generation, to be able to take a 300 kilowatt laser onto this test bed we're making. The 300 kilowatt lasers are already made. 2 contractors have successfully demonstrated 300 kilowatts with thousands of seconds of total time of lasing with no failures. Never seen a missile do that. And in realistic dwell time type scenarios, 30 seconds on, 30 seconds off, 30 seconds on, for hundreds of seconds. So they're very reliable. So I do believe this is a revolution, and you got me going, so I'm going to stop.
All right, Brian, from the academia and design engineer and the science behind that perspective, how do you see the focus in your field as helping to move that forward, both to what we can field today and then also where we may want to look at strengths, weaknesses, or future fielding and then tests based on what Dave said about what's available right now?
Thank you. So there's actually quite a lot to unpack there. And so my own research is dealing with basically modeling of laser engagements. And one of the major pieces of that is materials. Now, we talk about different laser strengths and what kind of targets you can take down at various strengths, et cetera, and there's a whole lot of ink that's been spilled on that. But the bottom line is, the higher the power, naturally, the better ability to laze through. And so the material aspects that are going to be seeing in a target are going to be extremely important. So one thing we talk about is the around 300 kilowatts is when they're expecting to be able to take down a cruise missile with a side shot. So basically penetrate the side of one of these cruise missiles. That's what was put up on the slide earlier. So and they say that to get around something that's an inbound missile coming straight at you, you need to get around a megawatt. Well, why is that? One of the major differences is the materials involved, okay? So the side of a cruise missile is typically going to be made of some sort of aluminum, and aluminum is fairly easy to melt through. Contrast that to the nose cone. Okay, nose cone is going to be something out of maybe like a slip cast silicate or pyroceram or some other sort of material, depending on the missile, okay? And because that's a ceramic, it has completely different melting characteristics. Okay, so if your whole idea here is to melt through a target to be able to cause some sort of effect, having something with a high melting point obviously is going to have it's going to be a much greater challenge. Okay, then if you want, some people are saying, hey, let's maybe see if we can use lasers against hypersonics. Well, that's an even more difficult problem because you're going to have more advanced materials that are going to be involved in that. Those are things that are designed to be handled at very high temperatures, and of course, hypersonic missiles are at high temperatures. So really, there's a lot of materials research that has to go in here, and there's a lot of understanding of how whatever laser power gets to the target, can you maintain that power on that target long enough to be able to impart the effect you have based on the actual characteristics of the target.
Joe, from the operator's perspective, near and dear to your heart and mine, how do you see some of the challenges and how have you seen some of the challenges with regard to fielding some of these systems and then how it may translate to near-term conflict?
I question the ability of a laser system to meaningfully impact an anti-ship cruise missile fight in the near to midterm. We're looking at relatively short ranges of lasers in terms of effectiveness, and on my notepad math, 600 knots is 1 mile every 10 seconds. So if we're looking at a 2 to 3 mile range and a 5 to 10 second dwell time in order to have effect, we're talking here about crossing shots, which are defensive assets are not that close to carriers in a meaningful context, and we're not going to be able to have the ranges to affect crossing shots with the 5 to 10 second dwell time, longer dwell times requiring for nose-on shots and a point defense capability potentially double or triple the length of time. We're suddenly out of time before that missile hits the ship. So even as a complement to kinetic defensive systems, I question the efficacy of lasers and meaningfully impacting that in the near to midterm.
Okay, and in our pre-discussion, one of the things that really came up and what I think we all need to iterate on, and Mr. Keel mentioned it in his remarks, is none of what we're doing has to be mutually exclusive of each other, and I think that's really important that we look at that. It's not you're only in the camp of directed energy and hypersonics. There's no utility for currently fielded technology. One of the things that I've struggled with in doing this for going on 21 years now is being able to effectively translate what the system's capabilities and limitations are, which a ton of brain power and a ton of work goes into, to being able to have the operator and the end user on the ship being able to effectively employ it. So, Mr. Keel, if you could elaborate some on what you may have seen throughout some of the testing and development, if there's consistencies that we, either through industry or through training and technology, are looking to leverage, or if this is kind of a system of Gucci systems, if you will, where everything's exquisite and kind of does its own thing. Sir?
That's a broad question. Let's start with the industrial base. All our existing DoD lasers are fiber lasers that are beam combined either incoherently, which is really easy, spectrally or coherently combined, which is a bit harder. The two 300 kilowatt lasers, one's spectral beam combined, one's coherently beam combined. They're using, the one contractor makes their own amplifiers. The other one uses off-the-shelf amplifiers that are mildly modified from what they use in factories. So that industrial base is actually pretty good because lasers are used in manufacturing extensively and they're highly, highly reliable and rugged. What isn't a good industrial base and which isn't necessarily highly reliable and rugged are all the optics to control the beam and get it out and focus on the target. That is a lot of cottage shops for a lot of the optics, and some of these optics are things that we call fast steering mirrors. They just jitter just a couple milliradians, maybe a couple hundred microradians, and that's how we help balance the beam and get jitter out of it. That base is not really there robustly. If you want to go to adaptive optics, which is a way of mitigating atmospheric turbulence, the deformable mirrors that kind of can correct for those phase distortions are very expensive and very Gucci. So the laser's pretty tough, but the optics aren't. From a ship platform integration perspective, like I said, a 300 kilowatt laser takes a megawatt of power. That's going to be challenging on a DDG Flight 2A, but all the studies done so far, there is definitely enough power and cooling if you use an energy magazine and a thermal magazine, or we do some exotic things that down in the weeds I won't go into here. It's doable. It's whether the Navy can afford to do that with respect to all the other things they want to do to Flight 2As, which includes some major upgrades in its life. And that may take away some of our service life allowance, which is how much reserve there's left on the ship. Did I kind of get that?
Yeah, absolutely. Mr. Blau, you've been working in this field and related fields for a significant amount of time. What's your perception of, have we improved in the ability to close some of these loops and back up the warfighter and the research and development side of the house from academia, or are we still kind of in the wrong supported and supporting relationship where we're constantly in a tail chase?
Yeah, so when I first started working in this field more than 30 years ago, and back when Dave was a student with us, the students used to say, hey, we could really use this out on the fleet. When are we actually going to have these on the ships? And it was always 15 years in the future, and it was always X plus 15, and X kept increasing. But actually, as I mentioned, I actually got to go out and witness a laser shot on a ship. Now, admittedly, it was just a one-off system, the SSLTM, but it shows that it is possible to do it, and it is possible for them to, and we've seen examples of them shooting down targets. There are videos out there you can even see on YouTube of them shooting down UAVs. So the progress has definitely been made over the years, but there are still some challenges to do. I mentioned I did a lot of work in the atmospheric aspect of it, and there are different atmospheric effects, absorption, extinction, that affect the laser beam. Turbulence, which Dave mentioned, you can correct for that with adaptive optics, but it's difficult and expensive to do. Another big issue is thermal blooming. And that's going to be a problem when we start to scale these up to the higher powers. That's where, as you heat up the column of air that the laser beam is going through, it causes it to defocus. And that becomes more of a problem when you start getting up to like these 300 kilowatt and higher systems that they're talking about going to for some of these threats. And so those are all things that need to be studied and addressed as we keep progressing this towards being able to have the power of capability to address some of these threats.
Thanks. Mr. Keel, from your standpoint, are we prioritizing directed energy specifically and/or directed energy tied with hypersonics effectively in the sense of accelerating and really you can think about either of these things as a kill chain, right? From idea to proof of concept to fielding, or are we sitting in kind of a lag pattern where we field things one-off? We're not operating to the maximum efficacy that we could to be able to push forward in this field.
What was this subtle specific there at the end?
Or maximum efficacy in pushing the technology forward to fielding.
Okay, the Navy is definitely interested. However, they are not at this point willing to press the ka-ching machine and get a lot of cash, because it's going to be about $1 billion, roughly, give or take, to field the first true program of record laser. And that's why we've been experimenting so much. We got 5 Odins out there. We got 1 Helios. 2 of the O&R lasers actually went to sea. The original was Laws. It went on the Ponce. SSLTM went on the Portland. So we're experimenting because there is a lot of, we got to overcome the people who think that they don't work that well. And that's why we've been pushing really hard to field these prototype systems to overcome some of that, I don't want to say resistance, but to learn how to use them. Kind of along the lines of how long the Navy's been involved in lasers was back in the late 80s with the Miracle laser, which was a very big laser, totally unfieldable. It shot down a lot of surrogate cruise missiles, and it shot down 1 Mach 2.5 target in about 2 seconds in a tactically relevant situation. So we know we could do it, but that was a laser that kind of the size of this little area right here. So it wasn't fieldable. Well, since then, the Navy took a long hiatus, and suddenly industrial base came up with much cheaper lasers, much more reliable and rugged lasers, and that's the fiber-based lasers we have today. So now is the time to get them out in the fleet in limited quantities and experiment and find out what they really can and can't do so that we can validate our models and simulations and all that sort of stuff.
Brian, I know sometimes some of this you can't talk necessarily specifics, but in your side on modeling, do you feel like you're getting appropriate level of access to information, testing, and being able to help in a collaborative manner move the field forward, or are you sort of on a voyage of discovery where you're having to find a lot of these things out on your own?
I have to say it has been actually pretty good. I've been getting a lot of support, particularly from the warfare centers, because I mean they've been investigating this for a long time. They have a long, and I guess you could say, vested interest in making this work. So Dahlgren has been especially wonderful. I want to give them a bit of a shout out in terms of helping out with this. But it's really important, a lot of the work they're doing. And again, kind of circling back to what Dahlgren has been doing, one of the pieces that they've done, I mean, they've done a lot of work. They have basically Lethality Lab that is doing a lot of testing on this sort of stuff. You see they have a lot of work with the combat systems piece, again, because the combat systems piece is especially important. The fact that these lasers again don't exist in a vacuum. Okay, they're again going to be part of an integrated layer defense, and what they do is they bring you this additional capability, which is supplementary to your kinetic weapons. And so having the labs essentially work hand in hand with the development piece, and me essentially as a PhD candidate latching onto that has been phenomenal. Just being part of that whole nexus.
Okay, we'll turn it over to the audience at this point in time. If there's any specific questions that you'd like to ask, there's a microphone here at the front of the aisle, or we'll be able to bring the microphone to you if anybody has anything they'd like to address to the panel.
Yeah, if I could just prime the pump, a lot of the conversation so far has been focused on lasers, and I was curious if any of you had any expertise or insights into high-powered microwave weapons.
Yes, but I won't talk about it here.
So I think some of what, and obviously ground rules, classification level, and what we can and can't disclose in this environment. I know there is certainly some open source information available about both. One of the analogies that was brought up at the beginning and something that resonated with me is if you think difference in efficacy, think a sniper rifle and have to constantly point and designate and be able to steer, stabilize, et cetera. That's kind of your field of lasers, where high-powered microwaves, some of the other systems can be more like a shotgun, where you get a much larger field of potentially defensive or offensive capability there. And I think, again, the key in a lot of this, in my opinion, from the operator standpoint, is I don't want stovepipes in research and development to where we say we can only have one or the other. But eventually, at some point in time, Royal, we have to decide on what we're going to field, and we have to make sure that the operators on the ships, aircraft, and submarines are fully trained and aware of the capabilities of what their systems can do. And then larger picture, that we don't build a bunch of one-off capabilities to when at the operational level, we're nugged down into those details of, do I have this capability resident in my force or do I not? And I think those are just things that we really have to make sure we keep in mind as we move these things forward, test it, field it, and then the program of record piece, which has been mentioned a couple times, really speaks to how it's going to integrate into the weapon system, and then how we continue with both layered defense and being able to offensively fight when called upon to do so. Does that answer your question, sir? At least to an extent?
I will add one thing. Lasers aren't the best small swarming UAV target because of their serial nature, but HPM kills very fastly those small UASs. It's pretty effective against them. Again, very short ranges, kills them very fast. I think it would really help in a swarm. And there is a lot of research in that area. Most of that is unclassified, actually.
Mr. Sitgraves.
Indeed. Damon Sitgraves, I just had a real quick question about all this energy that we're talking about, particularly for the far future aspect. I'm curious about the potential health effects, particularly the folks that are on those ships, of those high energy weapons, if that's been considered or if there's any studies on that. I'm really curious if that's a problem that we've come across as we've been testing these like lots and lots of, gigawatt energy type things.
Having been involved with the fielding of laws and the fielding of SSLTM, not too much with Odin or Helios down there. We go through all the safety and health effects and get certified for shipboard use. There is still some concern about, and I'm behind the power curve because I haven't been following the latest on this, on what the policy is for eye safety when you're topside on a ship and you're shooting.
Sure.
There are cutouts to prevent it from ever aiming back at the ship, but there is still the potential of some light coming out at a slight off angle just because of diffraction and scattering. And so far we have not had a problem with that aspect. And that's the biggest aspect of lasers, is unintentional blinding. But you really almost have to hit the person. There's so little light that scatters. There's been some analysis of a sphere, a rough sphere, how much really comes off it, and the eye safe distance, and I can't remember the size of the laser they used in the simulation, but it was big. It was, tens and tens of kilowatts. The eye damaging light coming off from a scattered diffuse reflection was very small, and the safe keep out zone was like 10, 15 meters. Specular is a different story, but then you have to have a very high, you're going to have a very lucky reflection to get
Certainly. Thank you.
One of the other things that came to mind just in talking through this is we talk about the energy required for these weapons and capabilities. We talk about air, power, and water, especially as it relates to what an organic ship can produce versus potentially land-based sites where you have less limitation there. Is that something when we do kind of creation to testing and fielding, are we appropriately taking those things into consideration and then building that into the fielding plan? Or is that sort of an accidental discovery and no snark intended of, oh, hey, this would be great to have, but we just can't produce enough power because all of the other great to haves that we've chosen for that specific instrument to implement the weapon?
So I can actually take that. So one thing that I'd like to point out is that these are specifically designed with shipboard integration in mind, okay? With the understanding that, let's just say we talk about, say we have a 150 kilowatt laser, 150 kilowatt output. So say it's 25% effective. That means that that laser is going to need 600 kilowatts of power to actually operate, okay? Now, if you're cruising about in your ship and you suddenly flip on a 600 kilowatt load, talk about having the lights flicker. Might cause a bit of problems. So basically that's something that has to be specifically designed for. So one mechanism of doing that is effectively, in a manner of speaking, isolating the laser essentially from the rest of the power grid, so to speak. So what you could do is basically integrate batteries. So you can have batteries, you make them be lithium batteries, or you could have lead acid batteries, or you might have something like flywheels. There's a whole bunch of different options for. But there is a lot of energy storage research going into this for exactly that problem. And the idea is that basically when it comes down to charge the weapon, if you will, that basically these batteries will just continue to charge off of this, the shipboard power grid. And yes, they will be taking some degree of energy from the ship, but the thing is, by having these batteries there, when it comes time to flip on the laser, you can just discharge from the batteries instead of actually worrying about necessarily, putting this tremendous load on the ship's power grid very suddenly. Okay, so this effectively you can use these energy storage options, be the batteries or flywheels or what have you, and part of the reason that integrating these lasers on a ship is such a big deal is because you have to account for all sorts of things here. It's not just the beam director sitting on top. You have all the actual beam generation equipment down below. You have cooling aspects that have to be in there. You have to have this energy storage capacity. So these things are being considered, and so you really do have to take this holistic approach to how a laser is going to be impacting the rest of the ship before you actually conduct an install.
Mr. Keel, did you have anything to add to that?
I can add a few things. Space right now on a DDG Flight 2A is the biggest limiting factor, but 100% correct about creating harmonics rippling throughout your AC system if you turn on a 600 kilowatt load or a megawatt load. I mean, that's catastrophic on a ship for electronics. So you do isolate it. Batteries are the preferred solution right now. Lithium-ion batteries, the Navy's scared to death of because they occasionally catch on fire. Although fewer Teslas and electric vehicles catch on fire than gasoline-powered cars when you normalize for the quantity of vehicles out there. There is another very old battery technology that people kind of forgot about, and that's nickel zinc. And it's actually better for a laser than for cars because it has higher power density, and that's what's limiting us, is we need a megawatt on and off quickly. And the lithium-ion batteries, you got to make a much bigger one because they're very energy dense and not as power dense. So Hellcat is using nickel zinc batteries because everyone kind of forgot about this ancient technology. It's like 100 years old. I mean, it's an old technology. It's been around. We're going to make sure that you can really charge them, discharge them fast and stuff like that. So I believe we can isolate electricity well enough. Thermal, there's multiple solutions to it. One of the most creative one I heard is there's 3,000 gallons of ship's chill water, which is the water we use for air conditioners. And if you ran a laser for, I can't remember the time, it was like 100 seconds, you would raise the temperature of the air conditioning water by 2 degrees centigrade. So what? You strip off some non-vital loads down in the mess decks, aft steering, things like that, and that can be recharged in the matter of 30 minutes or so. NAVSEA is seriously looking at that as the heat or the thermal magazine for ships. So we are working very hard to try to minimize the difficulty of putting lasers on ships. The biggest problem is ships look big compared to airplanes, but they also are full of people, full of food, full of fuel, full of weapons, and there is not a lot of room left on a DDG.
I think the other thing we have to acknowledge is that when we do that, regardless of what the battery's made of, we are sub-optimizing some other system. Whether you take that out of the 5-inch magazine, out of VLS, out of the CWIS magazine, there's something we're now not doing because we put a giant battery on the ship, right? So there is a trade-off here, and as it relates to cooling and changing how the system is currently set up, that's not a quick process, it's not an automated process, it's not an easy process, and it's being done by an 18-year-old who joined the Navy 6 months ago. So we have to understand that NAVSEA and lots of really smart people figured out how to solve this problem, but it's being implemented by people that are 18 to 22. And we have to make it easier to do, and if it's hard, it's not happening, and it's not happening well.
Do we think that directed energy and hypersonics, is this a new version of an arms race, and are we kind of at the cutting edge in our military industrial complex? Are we in a lag role and sort of learning from others? And where do we think, from the panelists' perspective, we stand in terms of being able to not only understand and create the technology, but also field it? Not, of course, asking anybody for an intelligence assessment, but where do we see ourselves, or where do we view the world in terms of fielding this capability and moving it forward?
It seems to me we have a lot of work to do. We have a lot of work to do. I think that everybody can agree on that. There are some promising motions, I guess you could say, because there are a lot of systems. Unfortunately, I can't go into depth here because of the setting. But maybe I'd say more or less in the midterm time frame, we kind of be expecting capability to be added.
Mr. Keel, do you have any thoughts on that?
DARPA's HAWK program is out in the public, at least in the general sense that DARPA is developing hypersonic vehicles. They're exquisite, they're expensive, they go fast, but the difference between Mach 3 and Mach 5, think about it, just do a simple time difference. I'm not too sure it buys you that much in strike capability, but the desire always is, since you target something and the missile has to fly out at maybe Tomahawk speeds, it will be at a completely different space. But at Mach 3, it might be at a slightly different space. At Mach 5, it's kind of right there. So there is an advantage to speed. They also help survivability. It's also, they're very expensive. And since this came from the news, the one thing I remember out of all the news on Ukraine is the Russians claimed they fired one hypersonic missile, and it didn't hit its target. Now it's Russia. Take that for what it's worth. I'm not too sure hypersonics is a radical game changer because they're going to be hard to produce and afford in quantity. Maybe that's okay if you're just going to use them for the exquisite targets, and that's kind of it. I think there's more value. I think there's more, and this is purely my opinion. I think quantity is a quality of its own. If you get some missiles that you can afford thousands of instead of tens of, you will actually have a bigger outcome on the war, even though they're not as capable.
Yeah. And I'd like to point out part of the reason why hypersonics are such a challenge is because it's a difficult problem. From a design standpoint, any sort of hypersonic system has just got tremendous things it has to cover. I say, for example, the very fact that once you go past that Mach 5 point, you start basically developing a plasma sheath, for example, around whatever vehicle you have. And you look at any textbook, they'll tell you about this. But basically, that plasma sheath makes a whole host of issues in terms of things like communications and sensors and whatnot. Because think about back in the days of the Apollo missions, right? Whenever the Apollo capsule was coming back into Earth, they always had a communications blackout, right? And what that meant was basically you had that plasma sheath around the Apollo capsule that was preventing RF signals from going across. And it's the same kind of thing will basically form around any hypersonic body. So that's a challenge. Also, the materials, going back to the materials aspect, that's a huge challenge, okay? You have tremendous heat that you're having to deal with, okay? These things are moving at tremendous speeds. They're moving at speeds where the drag is immense. So how do you basically prevent whatever this vehicle is from melting? Okay, you need exotic materials. Exotic materials wind up being expensive, okay? And then once you actually start having that heat, you know, you have to think of how you're going to dissipate it. If you just basically apply a constant blowtorch to one part of that missile and just leave it there, you know, without taking the heat away, it's going to melt eventually, right? So basically, you have to have ways of dissipating that heat within the missile and transferring it within the missile, so that it doesn't overheat and just simply, you know, vaporize, if you will. So even hypersonic propulsion is tremendously challenging. You know, if you go back to the days of, you know, okay, we talk about the notions of doing a ramjet. A ramjet basically takes air that's, you know, supersonic, slows it down to subsonic speeds, then basically mixes it with air, and then, you know, ignites it and expels it out the back. So that's good and all when you're operating at slower speeds, but once you actually get to a thing where you're basically having to get a scramjet, okay, once you start getting up to those hypersonic speeds, you have to use scramjets. Now what that means is basically that air that enters through the intake is staying supersonic the entire way through. So that means you have to, in a very short period of time, mix your fuel, oxidize your fuel, burn it, and have all that burning occur by the time it actually exits what is a very short cylinder, okay? So you need high-end fuels to be able to do that. You need very careful making mechanisms to be able to do this. And because any sort of fuel that gets spent out the back of this, you know, and isn't burned, that's just wasted. So you wind up with a very, you know, a fairly low, what is it? It's a specific impulse for any amount of fuel because of this. And so there are tremendous design challenges that the ones I just mentioned are just a few, okay? But in order for you to take a system that we want to employ, be it a hypersonic cruise missile or a hypersonic glide vehicle, we have to be able to address all those things. And that means lots of funding, lots of tests, lots of very smart people working on it. And it is, unfortunately, a very involved process.
I've got a question on acquisition process behind this, because I'm hearing a lot on the research and development aspect, that even the test and evaluation. You know, you mentioned the Odin and Helios systems that are out there now, but what I'm not hearing, and maybe we needed more people on the panel to talk about this, but is there a champion across the Department of the Navy for this requirement, for the capability requirement, to get it from RDT&E to actually procuring some, you know, managing that requirement and then throwing money behind it and then procuring a system so that we can put it not just on onesies and twosies of ships, but we can put it on all the Flight 3s. We can put it on all the, you know, the DDG-1000s. We can put it on all the LPD-2s, right? That's, you know, is there a champion in the Navy right now for getting across that valley of death that people talk about?
Dave, do you have any thoughts on that?
No. He left the Navy about 2 weeks ago and was up at OSD, and it was Dr. Frank Peterkin. There are a cadre of believers in the Navy. There's probably a larger cadre of people who are in the wait-and-see mode, and then some that it will never be there. And when you're a senior leader and your plate is overfloweth with issues you have to solve, this one's a hard one to put a lot of time and effort into. The Navy does have a process right now called NIF, and it's an acronym within an acronym. It's NAV Plan Implementation Framework. Let's call it an IPT that crosses all the resource sponsors in OpNav, and they try to make sure they got all their SEAM issues solved. There is one for terminal defense, and lasers fit in that bin. And I worked very closely with 96. Dr. Peterkin did before he moved off to OSD, although he still talks to 96. IWS-2 is the Navy's program office where directed energy will reside. They were the acquisition agent for the Odin, I'm sorry, for Odin, but Odin was government built. Helios was contractor built, specifically Lockheed Martin, and they're there. I would say our acquisition community is not yet ready for lasers. I don't want to bring up the Army. I shouldn't speak about the Army, but they're in kind of the same boat. They had General Thorogood before he retired, who was a huge champion of lasers and has pushed the Army. And for a while, they got ahead of the Navy. Now I think we're about equal on number of systems fielded and tested and prototyped. And they had the same issues. The S&T community's all on board doing the R&D, the prototyping. The acquisition community is, well, where's the logistics? Where's the training? Where's the parts support? Where's, the CONOPS, the TTPs, and all that? So that's why the Navy is not going to do General Thorogood's, just leap ahead, take advantage of his 3 stars and push. And the Navy's going to do more experimentation with onesies and twosies until we get these issues resolved. That's my read of the tea leaves.
Joe, do you have something you want to add?
Yes, sir. I think the challenge is we're approaching this in a backwards direction. We're trying to find use cases for lasers that are a technology decidedly in their infancy as it relates to current tactical employment of weapon systems. What we should be doing is looking for a hole in our defensive architecture or offensive desires and looking to apply technology to solve that problem, whether that is mature technology now or looking to R&D technology in development to solve a battlefield problem. We're trying to find a use case for a laser and put it on chips, onesie twosies, to evaluate the efficacy of a potential solution that we quite haven't figured out outside of strict testing environments.
Any other questions from the audience?
So I have a question on lethality. I wonder if you could give a sense of where the main challenges are looking at the types of targets that you would engage. Is it more understanding the basic laser material interaction? Or maybe you can comment on the level of understanding for this is what I need to put into an ASCM or another target in order to have a certain effect. What are the main limitations?
Are you asking a countermeasures question?
I'm asking from if I wanted to accurately model lethality on a foreign missile system, what are the big gaps right now in understanding?
We don't own them, so you have to guess. That is the biggest problem. But in all honesty, their physics is our physics and their engineering is our same engineering principles. There are good guess assumptions you can make. Penetrating aluminum is not that hard. Penetrating fiberglass depends on how thick it is. It can be a little harder or a little easier. Penetrating high carbon epoxies with carbon fibers is harder, but it re-radiates the heat on the inside of the missile. So you may be doing damage inside the missile well before you get to, penetration. That is a very open subject and very active area of research. Dahlgren does most of it for the Navy.
Do you have any sense on the follow-on, assuming that you knew very accurately how to put a hole in a certain material?
Yes.
Then to the overall effect in the
and most missiles put the systems at roughly the same places. The seeker's always up front. The warhead's generally behind the seeker. The guidance control computer's usually behind that. And then there's a motor, whether it's a rocket motor or a jet engine. And there's fins and canards someplace.
So to his point, I give an example of a nose cone, okay? So a typical nose cone, you usually have your sensors for whatever missile it is. Say for example, it's one that works of, just radio frequency guidance. So say it has an active seeker, it could be anything, doesn't matter. So based on the fact that you're going to want to have that up in the nose cone, okay, you're not going to want to put, iron around it because that's just something that's going to reflect back, whatever it is you're trying to emit. You basically pick some sort of material that's going to be, permeable to that particular, radio frequency that you're trying to be sensitive to. So, there are specific materials then, usually some sort of ceramic or in some cases like various kinds of polymers that you might be using up there. And so, that would help you essentially narrow down. So if you want to say, okay, if I'm going to be handling, targeting this particular part of, a missile, so to be able to get its sensor or, something in effect, I can expect this range of materials to be in this area. And then based on that, we can say, all right, so here's what I'm actually going to put in my simulations and actually try to figure out how long it's going to take to engage it at such and such range. Does that answer your question?
Yeah, it does. Thanks.
Yeah.
All right, well, this was a really interesting conversation. I learned a lot from it. And I want to thank our panelists and thank Commander Holland for a great job as a moderator for the panel. Before you leave, if you would open up the West app and then just do a little bit of a review for the panel discussion before going to the next event. I'd appreciate that. And please join me in a round of applause for our panel members. And on behalf of AFCEA International and the Naval Institute, we want to thank them. And we've got a Naval Institute book that is titled From Berkeley to Berlin, How the Rad Lab Helped Avert Nuclear War. Gentlemen, thank you so much.